Hello and welcome to this video. In this video we're going to go through the last of the AS practicals. This is an electricity one. We're going to be able to determine the EMF and the internal resistance of a battery. Now in order to do this we first have to write down the equation that we're going to be using in order to formulate this experiment, and we know the only equation involving internal resistance that we know of is that the EMF is equal to the current times the total resistance of the circuit plus the internal resistance. Now, in order to actually calculate these things, the current is really easy to calculate. We just shove an ammeter in the circuit. The EMF is pretty easy to measure. We'll just put a voltmeter across the terminals of the battery, and big R is again pretty easy to calculate since we'll be given a known resistance, and then we will do things with that. And R will be a fixed thing that we're going to calculate. So in order to actually calculate this, we're going to have to set up a circuit. So the circuit is going to look something like this. So we're going to have a battery, and I'm going to put a switch directly next to this battery. Let me actually draw this battery with some internal resistance just to make it more clear. And we usually have a box around this to show that it's one component, where the battery has an EMF of epsilon and an internal resistance of R. I'm going to put a switch in here, and let's call this switch S, and then I'm going to have a voltmeter in the middle here, and then I'm going to have a resistor or a pair of resistors. But let me actually just have a variable resistor in this case. Okay, so I'm going to call this R. Okay, and actually I've forgotten I need to put an ammeter in here along some point. So let's put the ammeter there. So now this is our complete circuit of everything that we'll need to be able to measure both the EMF and the internal resistance. So the first thing that we can say is that if we leave this switch open, we're not going to see any current reading. So we'll say with switch open, there is definitely zero current. There are no current traveling through because this is an open circuit. We have a DC current, it can't travel through the gap. Hence, this voltmeter reading is just going to be reading the terminals of this potential. And now if there's no current traveling through this internal resistor, that means there's no potential across this internal resistor, which therefore means if there's no potential difference across this internal resistor, the reading that we have on the voltmeter must be the EMF reading. So this, with the switch open, we read that the voltmeter reads the EMF of the battery. Okay, and that's the easy part. That part's sorted then. We know what the EMF is, and so we have a starting point. Now we need to investigate how is this voltage reading going to vary when we start putting a current through. So the first thing we're going to do is open the current, open the switch so we have zero current, and then we're going to close the switch. So with the switch closed, we know what it's going to be measuring is the terminal PD. So there is now a current. So there, I'm just going to put current with a tick. So there is a current there. Now the voltmeter reads the terminal PD. Reads terminal PD. And what the terminal PD actually represents is the EMF. So the terminal PD, which I'm going to call PD with a T here for T for terminal, is actually the EMF minus the potential across the internal resistance. Okay, now what this means is we can use this value of the voltmeter reading with this EMF value that we already know to then calculate what the potential across this is. Since we know the current, we can use V equals IR to then calculate the resistance, and that then means that we have the internal resistance. Now obviously doing one measurement of this is not very useful. So instead we're going to take multiple measurements and then we are going to form a graph. So our actual method is that we are going to close the switch, vary R. Now, some people will, instead of varying R, will actually just use different fixed resistances, which is also fine. I think just getting a variable resistor and changing it is actually just a little bit easier, because you don't have to keep taking it out of the circuit and adding it in. But there is some uncertainty that comes with the variable resistor. So we want to vary R and measure the voltmeter reading and the current reading. So the voltmeter reading and the current reading. Okay. And so basically what we're going to do is we're going to vary this variable resistor until we have 6 different measurements. So let me not put that. So we want 6 different measurements of the ammeter and the voltmeter. So the voltmeter reading and ammeter reading, this should say, but it will obviously be reading the current. Different measurements. And what we're going to do with those is then make a table out of all of these values. So I'm just going to scroll down a little bit. So we want a table where we're going to record the potential that the voltmeter reads in volts. We're going to read the current that the ammeter reads in amps. And actually, we don't need any more columns than that. Whatever this variable resistance is, doesn't actually play any part in how we're going to calculate this from a graph, and you'll see why in a second. But it doesn't necessarily have to be fixed resistances of known resistance. As long as the resistance of it changes, it doesn't matter how much by. Okay, and as always, you want to specify your errors in a table. Now, what's going to happen here is we are going to then plot a graph of V against I. And when we plot this graph of V against I, we will find that we know that when there's 0 current, the voltmeter is going to read a maximum value, because that maximum value is the EMF. And as we increase the current or decrease this resistance here, we're then going to end up with so as the current increases, if we go back to this diagram quickly, if we get more current passing through this internal resistance, our terminal PD is going to drop, because the potential difference here, so the VR, is going to increase, which means that the potential difference across the terminals, the voltmeter reading, is going to decrease. Okay, so that means that we're actually going to get a linear graph that is going to look something like this. Obviously, you will have points with error bars on them. Not all of these points will perfectly fit this curve, but you will draw a line of best fit. And actually, you want to then work out the gradient of this graph, and the gradient of this graph is equal to negative the internal resistance, since this is obviously going to be a negative gradient since it's decreasing. So we need a positive value for R, so this negative is just to cancel out the other negative. And then we get a value for the internal resistance straight from this graph. Now, some of you might be questioning why this graph even works in the first place. Well, if we were to look back at this equation that we introduced at the start, we have this equation here. If I were to expand this, I'm just going to scroll down so I get a little bit more space. I have the EMF is IR plus IR. Now, IR is just the voltmeter reading, because this is exactly what we were reading on the voltmeter, but so is epsilon minus IR is equal to IR. IR is the resistance that we were reading across here, or is the potential that we're reading across this resistor, and I with little r is the potential we're reading across this resistor, or actually epsilon minus little r, I little r is the potential across this resistor, which therefore means that this is actually V is equal to V, and so we're just trying to measure how does V change with current, which we know is a V equals IR graph, and therefore if I write that as R times I, then R must be the resistance that's causing this change, which is the internal resistance, and hence this graph actually works. Therefore, you want to plot this graph, get your value, and then calculate all of your errors, and then you have the internal resistance. So this one is slightly more complicated than the resistivity one, but it's not overly complicated. So let me just run through this as a summary. All we're going to do is set up this circuit here. We're then going to, with an open switch, read what the 0 amps is and measure the potential for when we have 0 amps. Then we're going to close the switch, and we're going to vary R so that we get different current values. We want to read at least 6 different current values and voltmeter values. We will then put those into a table, plot those on a V against I graph, and the gradient of that graph will give you minus R, and actually the y-intercept would also give you epsilon. And there you go. That is how you want to calculate the EMF and internal resistance of a battery. Thank you for watching.